Your aldoses and ketoses actually occur predominantly as cyclic structures in solution, but not all of them. So most of your 4-carbon aldoses and ketoses can form cyclic structures, while all of your 5-carbon and 6-carbon aldoses and ketoses occur predominantly as cyclic structures. So this is because of the tendency of your alcohol and aldehyde functional groups to react with each other. So there are two alcohol molecules that can add to a carbonyl carbon. So for example, if we have here an aldehyde functional group, the first alcohol can add to this carbonyl carbon, creating what is called a hemiacetal. So in the hemiacetal structure, you have a carbon bonded to an OH and the same carbon bonded to an oxygen and then another hydrocarbon chain. The second alcohol molecule can still add to this carbon, replacing the alcohol with the OR chain. And this is called an acetal. The same is also possible for a ketone. So there are two alcohol molecules that can add to the carbonyl carbon. The first addition creates a hemiketal, and the second alcohol added produces a ketal. In the case of our monosaccharides, both of the alcohol and the carbonyl groups are located in one molecule, and the consequence is that a cyclic or ring structure is formed. So for example, we have here glucose. The OH in carbon 5 can add to the carbonyl carbon, which is carbon 1. So the lone pairs of the oxygen in the hydroxyl functional group can attack the carbonyl carbon. And then one of the bonds here, specifically your pi electrons, moves out. So it no longer becomes a covalent bond between this carbon and this oxygen. The pi electrons will now abstract a proton floating in solution, and it is mostly taken as this hydrogen from the original hydroxyl functional group. But in reality, it's just any proton floating in solution. Now, this formation of a cyclic structure by your monosaccharide creates an additional asymmetric or chiral center in our molecule. So because the carbonyl carbon or the carbonyl functional group is lost, this carbon 1 is now a chiral center. But first, let's take note, the product of this reaction is a hemiacetal. So notice, carbon 1 is attached to an OH. The same carbon is attached to an oxygen followed by a hydrocarbon chain, the R represented here. Now, carbon 1 becomes a chiral center, and it is distinguished from the other carbons. So remember, we have the term epimer. So it refers to stereoisomers that differ in only one carbon or in one chiral center. Carbon 1 is distinguished from epimers through the term anomer. So carbon 1 becomes what is called an anomeric carbon or an anomeric center. So how is the chirality generated? The OH or the lone pairs of the oxygen in the OH group, when it attacks this carbonyl carbon, so this carbon now becomes an sp3 hybridized carbon. Now the oxygen can orient itself either above the ring or below the ring. So in the end, we have two possible products of the reaction. We have one in which your hydroxyl group attached to carbon 1 is found below the ring or the plane of the ring. And the second product is your hydroxyl group attached to carbon 1 is found above the plane of the ring. So to distinguish these two anomers, we have the alpha and the beta. The alpha is for the hydroxyl group positioned below the plane of the ring, and beta is for the hydroxyl group positioned above the plane of the ring. Now, these structures, once your monosaccharides form these cyclic structures, they are now designated as either pyranoses or furanoses. So pyranoses are for six-membered rings regardless of the identity of the elements found in your ring. So for example, your glucose, we have seen it form a six-membered ring composed of 5 carbons and 1 oxygen atom. So this name comes from the molecule pyran. So because the structure resembles that of the molecule pyran, they were called pyranoses. And we have furanose for 5-membered rings. An example would be the ring formed by fructose, which is a ketose. So this is because the structure resembles the molecule furan. Now notice how the rings were drawn here. These are called Haworth perspective formulas. So in the Haworth perspective formula, we draw the hexagon. So that's the ring or the pentagon for the furanose. But we have some of the lines in bold. So they are thicker. There are thicker lines. And these thicker lines are the bonds that are nearer to the reader. So if we imagine this plane as perpendicular to the plane of our screen, then carbons 2 and 3 are the nearest carbons to us, including the hydrogen and hydroxyl groups attached to them, followed by carbon 1 and carbon 4, and then the farthest are the oxygen in the ring and carbon 5. So these are your Haworth perspective formulas. So if your glucose, for example, glucose assumes this cyclic structure, it is now called a glucopyranose. So it's in the D, it's the D isomer, and we have the alpha anomer. So how do we draw Haworth perspective formulas? So let's go back to the linear structure of glucose. So we have the aldehyde functional group. So we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So in drawing the Haworth perspective formula, first, you need to know whether, first you draw the skeleton. So the skeleton would be the six-membered ring. Next is you need to determine which type of anomer is it. Is it the alpha or the beta? If it is alpha, then the OH should be below the plane of the ring, as shown here. And then, is it the D or the L isomer? So for that one, we will be looking at carbon 5. Okay? If it is the D isomer, then we draw it by placing carbon 6 above the plane of the ring. And now, the final rule is that if in the Fisher projection formula, your OH is found on the right side, then it should be below the plane of the ring. If it is on the left side of the carbon, then it should be placed above the ring. And then the next one for carbon 4, it's on the right side, so it should be below the ring. And this is how we draw our Haworth perspective formula. This is alpha D glucopyranose as shown here. So let's practice by drawing the Haworth perspective formulas for alpha D mannose and beta L galactose. So let's start with alpha D mannose. So as a reference, let's draw first the linear structure of alpha D mannose. And then let's proceed by drawing the skeleton of our Haworth perspective formula. So it says it's alpha. So the OH in carbon 1 should be pointing down. It's the D isomer. So carbon 6 should be above the plane. And then the rest. So for carbon 2, it's on the left side. So this should be pointing up. For carbon 3, pointing up. And for carbon 4, pointing down. So this is the Haworth perspective formula for alpha D mannose. Next, beta L galactose. So again, let's draw first the linear structure of beta L galactose. So this is the L isomer. Therefore, for carbon 5, the hydroxyl should be on the left side. Then let's draw the skeleton of our Haworth perspective formula. This is the beta anomer, so the OH should be pointing up. This is the L isomer, so the CH2OH or carbon 6 should be pointing down. And then for carbon 2, OH is pointing down. Carbon 3, OH is pointing up. And carbon 4, OH is pointing up. So this is our Haworth perspective formula for beta L galactose. Now, your alpha and beta anomers can actually interconvert in aqueous solution. And this process is called mutarotation. So it's possible for the linkage of the oxygen and carbon 1 to be broken, and this will allow the OH to flip. So from the anomer, it can flip to the beta, or from the beta, it can flip to the anomer. So remember, a bond is needed to be broken for the alpha and the beta anomers to interconvert. So in mutarotation, a bond needs to be broken. So for example, if I start with a solution containing purely beta D glucopyranose, after some time, it will actually be composed now of different types of glucose. So 1/3 of the glucose in solution is the alpha anomer, 2/3 is the beta anomer, and there are very, very small amounts of linear and 5-membered form, or the glucofuranose. Likewise, if I start with purely the alpha anomer of glucose, in time, it will produce the same proportions. So after some time, if I check the glucose in my solution, 1/3 of them are in the alpha anomer, 2/3 are beta anomers, and very small amounts of the linear and 5-membered rings. So it means that your beta glucose is more stable than your alpha glucose because at equilibrium, you have a bit more of the beta glucose than your alpha glucose. And why is that? So let's go to the structure of your pyranose ring. So this 6-membered ring is not planar in reality. So even if we draw them as, if we imagine them as a flat plane, that is wrong. So in reality, they tend to assume what is called a chair conformation, because this chair conformation is a relatively stable conformation for a 6-membered ring. So for example, we have a beta D-glucopyranose. So the Haworth perspective formula is this. So this is beta, so it should be pointing up. And then that's down, up, down, and CH2OH. So in the chair conformation, what you do is you first draw the chair. Okay. Now, if it is pointing up, so for carbon 1, this is pointing up. So this should be parallel to this bond. So we have OH here. For carbon 2, the OH is pointing down. So this should be parallel. It's pointing down. So it should be parallel to this one. For carbon 3, it's pointing up. So it should be parallel to this bond. For carbon 4, it's pointing down. So it should be parallel to this bond. And then carbon 6 with this CH2OH is pointing up. So it should be parallel to this one. And just put there our oxygen. So see how we draw the chair conformation by looking at the orientations of the functional groups. So I think this was taught in your organic chemistry class. So you should already be familiar with how you draw your chair conformation. And when we talk about chair conformation, there are two positions. We call the equatorial and the axial positions for each member of your ring. So for example, here at carbon 1, your OH functional group is at an equatorial position. And the other hydrogen bonded to carbon 1 is in the axial position. For carbon 2, the same. The OH is in the equatorial position and the hydrogen is in the axial position. It's actually the same for carbon 3 and carbon 4. And for carbon 5, your hydrogen is also in the axial position. Now this can actually switch. So what happens is that carbon 1 is now flipped upwards and carbon 4 is flipped downwards. And we get this chair conformation. However, in this chair conformation, we see that most of your bulky functional groups, your OH and your CH2OH, are in the axial positions. The axial positions are not favorable for bulky substituents because they are nearer each other and van der Waals repulsion becomes more possible, or the chance for van der Waals repulsions increases. So we prefer your bulky substituents to be in equatorial positions. Hence, this one on the left side, this is the more stable chair conformation for your beta D glucopyranose. Now for your alpha D glucopyranose, the only difference is that the OH group in carbon 1 is now occupying an axial position. But for the rest of your carbons in the ring, their bulky substituents are found in the in the equatorial positions. So this is still the more stable conformation for your alpha D glucopyranose.